Hello all. So let's look at how waves propagate in a guided medium. So that is our primary interest in exploring how one can confine light, propagate light and exploit this confinement. But light and free space, we have seen it, right from our school experiments, physics experiments. In undergrad, you must have done experiments in your physics labs, and also looking at some laser, right, used for some interesting application and also experiments. Free space is reasonably well known. The laser light going through free space, you don't see any divergence and so on, but they always follow a straight line. If you want to change the direction, we use mirrors to do that. But then it is okay to do that in setups on optical tables and so on, that reasonable size that you can handle. Imagine that you want to send information that's like 10 or 20 kilometers from here, or even add few zeros, right, hundreds or thousands of kilometers from here. It is impossible to align your laser with the receiver there. Maybe few tens of meters is still possible, but then the alignment becomes very difficult once you go out, and also the losses becomes beyond what one could accept. So the guided wave system is a much more sophisticated way of transporting light. So in a guided medium, meaning we take a dielectric, right, similar to optical fiber is a good example, and put in our photons inside. And once we design it in an appropriate way, we should be able to take this photon inside the medium to the other side. This other side could be tens of kilometers without losing that. So we need to keep it inside. We know a lot of light matter interaction that can go on. The two popular ones that we have seen is reflection and refraction, and you could also scatter, right? It's a combination of this. So once the refraction happens, light goes out of the system. Is it possible for us to keep the light inside the medium of interest, right? Once you can achieve that, we call that as a guided medium. So you can guide the light where you want. So let's look at what are all the requirements we have in order to do this, and also how are we achieving this, right? What are the phenomena that help us in realizing light confinement and guiding. All right. So let's dive in. So waveguides are three-dimensional structures. So these structures got what you call the dielectric waveguide, for example, right, consist of an arbitrary shape, let's say, right. It's an arbitrary shape in x, let's say x and y, right, and this will be of infinite length, let's say. So they are along z, and this material that we have where we are going to confine is called core, and it is surrounded by a medium, right. The surrounding medium is called cladding. So optically, if we want to differentiate these two, so we can say N core and N clad. So the N core should have higher refractive index than N clad. This is a requirement. We will see I mean from where are we saying this. I mean, let's say you are arbitrarily saying that n core should be greater than n clad. Why not n clad is greater than n core, why not, right. So, there is a reason for this. We will see why we want this to happen, right. So, normally this is the requirement for guiding light inside the core. The light is propagating along z direction here, and the electric field is in x and y, which can be represented by your dielectric constant here, epsilon x comma y over epsilon naught. So, this is the dielectric constant that we have. It could be your isotropic, right. I am not going to differentiate isotropy and anisotropy here for all practical purpose. Let us right now assume for all the further discussion they are isotropic. So, wherever you move in the xy plane, the refractive index is uniform, right. So, that means your refractive index in nxy is uniform across this plane, and it is extruded along the z direction, all right. So, this is basically your arbitrary waveguide. So, there are two type of waveguides we have, right. So, one is a non-planar, it is a non-planar waveguide, and then you have planar. Okay. So, in a non-planar waveguide, we can already see that the name itself suggests it's not planar. Let me first explain a planar waveguide. So, planar waveguide is where the light is confined only in one transverse direction. Okay. So, let us say you have x and y. So, the light is now confined in the x direction. So, along y direction there is no confinement, right. So, the core is nothing but a sandwich, right. So, a sandwich between the two clad. So, you have core, you have two cladding. So, this is what we call a planar waveguide. Okay. So, we can also call this as a film, right. So, it is a thin film waveguide, right. This is nothing but a thin film, right, for all practical purpose, and you have a cover, right. Claddings are cover. Your glass window, right, for example, is a planar waveguide. You must have seen in some of the shops, right. You will see when people put LED light on top of this whole window or this glass will glow as if you have light source or light emitting from this window. No. So, you can put LEDs at the top, right, and this glass slab will act as a planar waveguide. So, you have glass and then you have air. This satisfies our condition for waveguiding, because the refractive index of glass is about 1.45 and refractive index of air is 1. So, that means n core, right, is higher than the cladding index. So, that is the reason why by putting LEDs on top we can make it propagate and shine, all right. So, that is a planar waveguide. So, this is a planar waveguide. So, let us look at non-planar waveguide. In a non-planar waveguide, so light is confined in two dimensional, a true dimensional transverse optical confinement. Okay. So, that is called the non-planar waveguide. So, here they both in x and y light can be confined. A good example is optical fiber, right, and the other example is a wire waveguide, right. So, where light is confined both x and y, all right. So, two dimensional confinement, and here it is one dimensional confinement. All right. So, this is the basic difference between a non-planar waveguide and a planar waveguide. So, as I mentioned, we could confine the light in 2 dimension and in 1 dimension. Let us look at how one can do that. Right. So, you can have a very thin film, right, take a thin film, and then we can extrude this, and this is the part. So, now light can propagate, right, inside the sandwich. So, you have N clad, and N core, right. So, this is N core. So, now when I put light can travel in this sandwich. So, as you can see, it is confined only in this vertical direction, laterally it is not. But then I can also take an example of optical fiber. So, here the light will stay inside this boundary, right. This is the core and this is clad, right. So, now I can confine this in whichever direction I want, x and y, right. So, this can extend, or in other words, if you really want, it is r comma theta. So, you can confine it in any direction angle you want. All right. So, this confinement happens along the cross section, and you can allow it to propagate, let us say in an integrated photonic circuit. It can be tens of micrometers to tens of millimeter, right, or even centimeter. In this case, right, you can even have it for hundreds of kilometers, for example. So, it is possible to do it, right. It is once you confine it, you should be able to allow this to happen. And the optical waveguides, right, both the fiber based and also the rectangular or rectilinear geometries are fundamental structures. So, these structures are key structures for semiconductor lasers, passive devices such as filters, wavelength division, multiplexing, and also active devices like electro-optic modulators or aquasto-optic modulators, and so on. So, this structure becomes really key to realize various functionalities that one can use it in many applications. So, the refractive index we defined here, N core, N clad, but it need not be strictly that way. All right. There is a configuration for that. So, that let us look at how the refractive index should be, right. So, there is index profile. So, let us just simply take a cross section, right. So, we took a very simple sandwich here. So, N core, N clad, right, and then N clad, let us say. All right. So, you can use other names as well. So, as a function of let us say the x and this is c. So, if I am going to draw the refractive index, right. So, this is refractive index, it's a function of distance. So, there is clad index and the core index like this. So, this is N core and N clad. So, this is what we call step index configuration. It is all like a step, you go from the clad to core. So, I could have something different here, right. So, again refractive index. I could have different indexes for core and cladding, both the cladding. So, I could have very low index here, high index, and something like this. So, here I have 3 refractive indices, you see. So, this is of course N core. So, this is N clad 1 and this is N clad 2. So, this is the top refractive index and bottom refractive index. Whether this configuration would work? Absolutely. The reason for this is the N core is greater than N clad 1 and N core is also greater than N clad 2. So, this is the condition that we should satisfy. If you remember, that is the first thing that we stated, right. So, your core refractive index should be higher than the refractive index of the surrounding, then only you can confine light. So, this is step index, right. So, we have another form or another profile which is called graded index. So, there is a graded index profile. We can take the same configuration here, right. So, there is N clad, N core and then N clad. The only difference here in the graded index is this N core is now a function of position. So, it is not anymore uniform refractive index as we saw here, alright. So, now the refractive index profile. So, here N clad is uniform, no doubt about it, and now this N core is now as a position dependent one. So, it could have anything. In this case, let us say it follows a parabolic function like this and then this. So, here the refractive index is profiled, it is graded, right. We call it as graded index waveguides or graded index profile. So, why graded index is important? Later on we will see once we understand light propagation and how light propagates through this thin slabs with the different refractive indices, we will attempt to understand why one would think about grading, which is not easy to fabricate, right, unlike the step index. We just sandwich different layers and we should be able to get it, alright. So, for a non-planar waveguide, so this is in planar geometry, you can also have this refractive index profiles in non-planar geometries as well. Let us start by understanding what are all these non-planar waveguides. So, we call this channel waveguides. So, channel waveguides are mostly we are talking about non-planar waveguides here. So, they are all non-planar. So, that means the refractive index profile, right, have both x and y. So, that is n x comma y, right, and you have confinement in both the direction. Confinement in x and y, right, in both the direction we should be able to confine. So, there are different kind of different types varieties of such waveguides one can come up with. One special type is this optical fiber, the circular profile, right. The rest of the things are rectangular, but this one is a special type, this is the circular type, okay. So, primarily we will only handle here non-planar that are channel waveguides. Okay. So, what are those? So, let us start from a simple buried waveguide, right, buried channel. So, here the core is buried inside the cladding here, right. So, this is N1 surrounded by N2, alright. So, here N1 is greater than N2. So, this is called buried channel waveguide. So, the waveguide is buried inside a cladding material. Okay. So, next is strip loaded. It is a strip, that is a loaded waveguide. So, the configuration looks something like this. So, you have a slab, alright, but then you have a refractive index N1 and N2. This is a slab, right. You can quickly judge that, okay, this looks like a slab, but it is a strip loaded. So, that means I am going to load this with a waveguide here. So, this has a refractive index N3, let us say, right. So, here the refractive index of N1 will be greater than N2, which will be greater than N3, which will be greater than N2. So, this configuration is called a strip loaded waveguide, alright. So, in some of the waveguide material, you will not be able to create such rectangular or square structure. So, that means you need to etch them and remove this in order to create this, right. So, if we are unable to do that, we can have a thin film deposited, and on top of that you could deposit your material of interest, that is easy to process and create this kind of channel. Okay. And this channel that you have, the strip that you have, will allow the light to be confined in this region. Okay. We will see how these confinements happen, but for the moment this is how you can confine the light. Alright. The next configuration is what we call a ridge waveguide. Okay. Ridge waveguide. So, ridge waveguide or strip or wire. Okay. So, these are all the three names you can give it to this. So, here we can take plane index and then we have a waveguide defined on top. So, this is N1 and this is N2. So, now the light will be confined within this region. So, light will be carried in this particular region. Alright. So, this is a strip waveguide or a wire waveguide or a ridge waveguide. So, the next thing is a rib waveguide. A rib waveguide is a little interesting. So, here we have vertical and horizontal confinement, but you can see here the material with refractive index N2 is made as a wire, right. But in this case of rib, right, we are going to have a shoulder. So, we are going to have the shoulder of this waveguide. So, this is your N1 and this is N2. So, they form a very nice shoulder that allows the light to be confined within the N1 region. So, again here N1 is greater than N2, here again N1 is greater than N2. So, this rib waveguide got these shoulders. Okay. There are few implications on having this shoulder. Sometimes it is very useful, which we will shortly discuss, but this is again another class of waveguide where one can confine light. Okay. And there is one more waveguide configuration which is called a diffused waveguide. Which is very popular with the lithium niobate based system, where you take the material and then diffuse a metal, for example, inside it. So, there is a metal diffusion, and this diffusion will cause a buried, it is similar to buried waveguide, but not fully buried. You see, in a buried waveguide, the waveguide is sitting completely immersed in the cladding, right. But then in this case you have the surface, right. So, the half of it is sitting inside, and this is called a buried diffused waveguide, where you could create this refractive index contrast by diffusing a material. In lithium niobate, it's titanium diffusion that people use. There are other platforms one can also realize by this diffusion. All right. So, but primarily the popular geometries when it comes to silicon or silicon nitride or 3,5 semiconductors, we will use one of these 4 configurations that we saw: a buried channel waveguide, strip loaded waveguide, ridge or wire waveguide, or rib waveguide. So, these 4 are popular configurations that one can use. Let me quickly touch on why this strip and rib waveguide configurations are required. So, of course, we understood strip loaded, why, right, because of the processing difficulty that you may have for this material, the waveguide material that we have. But wire waveguide, you want to confine the light in N1. It is done perfectly well here, but then in a rib waveguide you have a shoulder, right. So, the reason for this is in some of the application you want to apply some electric field. So, you want to apply a field through this to change the material property, let us say, in order to realize electro-optic or acousto-optic effect from this material that you are using. That N1 material could be a nonlinear material, right, anisotropic material, where you want to exploit their property by applying external field. It could be electric field, it could be thermal, right, it will be acousto-optic. So, any of those effect. So, in order to apply that, you need to have this material extended, right. So, that extension is given by this rib structure, all right. So, those are all the different waveguide platforms that we can exploit. So, when it comes to the waveguides, right, there are different polarization that you can allow in this particular system, right. In a non-planar dielectric waveguides, right, primarily they support distinctive modes or distinctive solutions into it. So, the important thing to understand is in a non-planar waveguide, you expect to see hybrid modes, right, in addition to pure TE and TM modes, right. So, TE and TM are very distinctive electric fields, right. So, you have orthogonal fields here between TE and TM, but in a non-planar waveguide you will see hybrid modes. So, what do we mean by that? Is a certain percentage of TE or certain percentage of TM in a solution, okay. So, that is what we call a hybrid solution, and that is the reason why we do not call it as TE and TM anymore. We call it as quasi TE or quasi TM. So, we just say QTE, QTM. Tm. So, they are not purely electric or purely magnetic. We will see this when we solve for our wave equation inside this, but this is something that you should all keep in mind and understand that there is no pure Te or pure Tm like in other waveguide systems. Even in a planar waveguide system you could have pure Te and Tm, right, but not in a non-planar configuration. And the other thing is, for a non-planar configuration, there is no, we do not have any analytical solution, right. So there is no analytical solution, right. So to capture the nature of the modes here, because of the structure itself. So it's not possible to do that. We have to do this numerically, right. So we use numerical methods to solve this. For example, beam propagation. Beam propagation method is one such technique to solve this numerically, and there are a lot of approximation that one can do, right. So one of the approximation method is effective index method and so on, okay, which we will see later on. But this is brief description about waveguides and waveguide configuration, right. In the next topic we will look at waveguide modes, how light can be transported in this medium. So right now we understand the geometry, right, what is the geometry required. So for some of you are very used to the circular fiber based geometry. So we also have planar geometries, particularly for photonic circuits. So with that we have covered a different type of, or rather class of geometries we can use, and in the following class we will look at what are all the modes or what are all the solutions that can allow us to propagate light through this different geometries. Thank you.